Introduction to Organic Chemistry. I should turn that light up. So, as I've said, today's 2 lectures and then the 1 lecture tomorrow that you're going to have after the test will be on sort of starting to look at some stuff to do with organic chemistry. And like I've already said, it's not going to be, here's 60 reactions to memorize by morning, because it's not the way we do it here, right? The types of molecules that we call organic molecules are the ones that predominantly contain carbon, hydrogen, and to a lesser extent oxygen and nitrogen. Right? So organic ones aren't sort of inherently better for you because they're natural, not like an organic potato or something, but they're ones that contain predominantly carbon and hydrogen, but normally also nitrogen and oxygen. There's only a handful of organic molecules that are really just carbon and hydrogen. But I suppose the point is that in these molecules, the molecules have a central skeleton or a central framework, if you like, and that framework is made up of carbon atoms joined together. Right? So unlike CO2, which is just a single carbon atom with 2 oxygens attached, you wouldn't call carbon dioxide an organic molecule, even though it's only got carbon and oxygen in it. Whereas a lot of these other things, sugars and oil and that sort of thing, you tend to call organic because they've got lots of carbon atoms joined together that form the backbone of the molecule. Organic molecules are the ones that we find in nature, right? And these seemed, back in the day, to have very different properties to unnatural ones. So again, imagine you're going back 250 years, sort of 1750, 1760, that sort of time, and all you had really available to you to analyse molecules was a furnace. Maybe a little bit Bunsen burner, a little bit flame tests and stuff by then, but most of the times people just had a furnace to decompose stuff and try and work out what it was made of, right? So if you take a piece of sugar and you heat it up, what happens? Yeah, it goes black and sticky and nasty. And if you cool it down again, what do you get? Yeah, it's still dark, it's still, well, it's tacky now or solid, but does it look like what you started with? No, right? If you do the same thing with a piece of copper, you heat up the piece of copper, the copper will melt eventually, but then when you cool it down, you get the same stuff back, yeah? And so people thought that this meant that these molecules that came from nature were different somehow from these other things, because when you cooled them back down, they didn't come back to the way they started with. And so what they said was that these molecules that came from nature must have something in them that when you heat them up is lost. Okay, you drive something off the compound in the process of heating it. It bubbles away, if you like. And so they called this thing the vital force. And it was believed that the thing that distinguished organic molecules from inorganic molecules was this vital force. Right? And that was somehow related to the fact that sugar is something that you use in your body to keep you living, whereas you don't tend to eat copper. It doesn't really help a lot. So they thought that there was this very big distinction between molecules that came from nature and molecules that came out of rocks in the ground, right? The metals and that sort of thing. And it was this guy, Friedrich Wöhler, who was the one who first showed that in fact that wasn't true, because what he did was he took an ionic compound called ammonium cyanate. Ammonium cyanate looks like this, NH4CNO. So CNO minus is the cyanate ion. It's not one you've probably come across before, but ammonium cyanate, which has all the properties of an inorganic compound, and he did a reaction on it, and he turned it into urea, where urea is that stuff. Sorry. It probably should be actually be better at that. And he turned that into that. And obviously urea is a natural compound because urea comes out of your pee. Right? People knew that at that stage. And so a very natural organic compound coming from a very inorganic compound. And so if you like, this is one of the very first organic syntheses, but it was also an important result because it showed that in fact you can make anything from anything else. There isn't this big divide between molecules that contain the vital force and molecules that don't. Right? So this is one of the very first organic syntheses, and from that there are now gajillions of organic syntheses that are known. Right? And so this is one of the reasons why I get a little bit grumpy about the high school chemistry, because they make you learn these reactions, but why not those ones? Right? You learn you can make an acid chloride with thionyl chloride, but why not by reacting with one of 20 other things? It seems like it's a bit randomly chosen. There are thousands of reactions known now, and there are millions of organic compounds that have been made that do not exist out in the world, that have been made by chemists that are new. And the books that summarize these reactions are big. Probably the standard one in terms of a book is a book that's about that big, by about that thick, and there's 13 of them in the series, which summarize all the organic reactions that were known at some point about 10 years ago. These days, of course, it's all online databases, and you can search online databases. You can stick in that goes to that, push search, and it'll spit up every report of every reaction like that in about 5 seconds. It's fantastic. But it didn't used to be like that. So there's just heaps and heaps and heaps of organic reactions out there now. And if you want to be an organic chemist, then you kind of have to have a feel for a reasonable chunk of them. But what you find is that in order to understand the properties of these organic compounds and how these react, we use the same sorts of ideas that we've already been talking about. Because remember we said back last week that there's really only 3 types of chemical reaction. There's precipitation reactions, there's acid-base reactions, and there's redox reactions. And that applies to organic chemistry as well. Right? At the end of the day, we can understand all the organic reactions in terms of those 3 things. It does mean we have to slightly modify our definition of an acid and a base, but we'll come to that tomorrow. Yeah? And so we're going to hopefully, and this is what I want to do, I want to try and show you how you can understand these organic reactions, not by just merely memorizing them, but by recognizing what sort of reaction that they are, and by understanding how that reaction works, you can apply that understanding to any other chemical reaction we might throw at you. Right? So let's start by looking at the simplest organic molecule you can, which would be methane, which is just CH4. We saw methane right back in the first week. What do we know about a methane molecule? Well, what we know from when we did the lecture on bonding and Lewis structures and stuff is that methane consists of 4 carbon-hydrogen bonds arranged in the shape of a tetrahedron. Right? So remember the angle between those carbon-hydrogen bonds is about 109 degrees. So it's a wee 3-dimensional shape. Now I've got this thing here which is in brackets, but probably shouldn't be in brackets. It probably should be in like 80-point font, bolded. In a stable organic molecule, carbon will always form 4 bonds. Right? In all of the organic chemistry that you do, if you are drawing out a molecule that has a carbon atom, that carbon atom should have 4 things attached to it. If it doesn't, then it's not going to be a stable molecule. Now, we're going to see instances where that's fine because you can make unstable things on the way to making the product. But if it's a product or a reactant that you're drawing, it should always have the carbons having 4 bonds. Sometimes 3, like I say, never 5. There are about 7 compounds known in the world where carbon has 5 bonds, and you won't see any of those this year. Right? So carbon always has 4 bonds. And you know why that is, if you remember back to that Lewis structure stuff, because carbon has 4 valence electrons to share in making covalent bonds with 4 other things. Yeah? Are the bonds polar? We talked about polar bonds back in the first week as well. The way we determine if a carbon-hydrogen bond is polar is we look at the electronegativities of the carbon and the hydrogen. Yeah? So we look those up in a book. We don't memorize them, we look them up. And we find that the electronegativity of carbon is 2.55 and the electronegativity of hydrogen is 2.20. So they're very similar to each other. And so the way that we need to interpret that is we say because the difference in the electronegativities is very small, that means that the electrons that form the carbon-hydrogen bond are pretty much going to be equally shared between the carbon and the hydrogen, and so we would say that these bonds are non-polar. The bond energy of a carbon-hydrogen bond, see how we're tying in all these different things that we've learned back in earlier lectures to all try and understand the particular properties of this molecule. So we talked about electronegativities to understand whether these bonds are polar or non-polar. The bond energy of a carbon-hydrogen bond is also quite high. It's 438 kilojoules per mole. That's quite a big number, right? They only get up to about 600 for a bond energy, so these are quite strong. And so these two things mean the fact that the bonds are quite strong and the fact that they're non-polar, these two things combine to mean that a carbon-hydrogen bond is quite unreactive. If you want to do a chemical reaction that involves breaking a carbon-hydrogen bond and replacing the hydrogen with something else, then that's going to be quite hard to do. And so if you're a methane molecule, which only has carbon-hydrogen bonds, then that means that a methane molecule is going to be quite unreactive. Sorry? The only thing you can really do with methane is you can burn it. Yeah. You can burn it and make carbon dioxide and water. But obviously that requires heat. You know, you've got to put a heat into it to get that reaction going. The other thing that you can do with methanol if you're smart is you can do this. Now, how do we do that? Actually, let's take the water out. Yeah? Is taking methane, reacting it with some source of oxygen and turning it into methanol. Right? If you can do this, then this is good because you can make fuel out of this. And so there's lots of plants, I think there's even a plant in New Zealand somewhere which does this. Takes methane and turns it into methanol. But this is hard, right? And you need fancy catalysts to do this, and it's one of these things where the amount of energy you put into making it is not that much different to how much energy you get back out using it as a fuel. So you go, well, what's the point? But lots of people will be developing new catalysts to try and do this sorts of reactions a lot easier. And of course there's bugs. There's bacteria that eat methane for breakfast and turn it into methanol. And so another way is you just grow lots and lots of the bugs and feed them the methane. Because the methane like bubbles up out of landfills and stuff. Comes out of cows as well, but it bubbles up out of landfills. And increasingly people are catching all that methane and trying to use it to make energy. All right. So, unreactive molecule, but still one that people are doing a lot of work and trying to make useful. So methane only has carbon-hydrogen bonds. Other organic molecules involve carbon-carbon bonds. But carbon-carbon bonds aren't much better, really, because obviously a carbon-carbon bond is non-polar because you've got the same atom at each end of the bond. So they've got the same electronegativities. Yeah? So a carbon-carbon bond is non-polar, and a carbon-carbon bond is quite strong as well. It's 346 kilojoules per mole. So not as strong as a carbon-hydrogen, but still pretty good. And so they're quite hard to break as well. Now note, this is referring to a carbon-carbon single bond, not a double bond. That's a different thing. We'll come to that a bit tomorrow. And so what we then find is that these organic molecules that we're going to be talking about are built from frameworks which consists of carbon-carbon and carbon-hydrogen bonds. And these frameworks tend to be unreactive. And so the reactivity comes from other things which are attached to this framework. But the framework itself tends to not be that reactive. Because these carbon-carbon bonds are quite strong, it means that you get organic molecules which have long chains of carbon atoms, where all the carbon atoms are joined together. So here's methane, and what I've done here is I've highlighted in red the first part of the name. There's this thing called organic nomenclature, which we're going to do more of after the break, which is a systematic way of naming these organic molecules. And so in this system, which we're going to talk more about later, we would call this methane because this compound has one carbon in it. And so this meth part, M-E-T-H, is the part of the name that refers to that having one carbon. You can get a molecule like this called ethane, where now we have two carbons joined together. Each of those carbons have the other three bonds, because remember carbon has to have 4 bonds in a stable molecule. And so each of the carbons has 3 hydrogens attached to it and then makes its 4th bond to a different carbon atom. So we have a carbon-carbon bond here as well, and this molecule is called ethane, so the F part refers to this having 2 carbons in the molecule. And then we can get bigger and bigger. We can go to propane, where now we've got 3 carbons in a row, so the prop part refers to 3, and butane, and so on. So these chains can get bigger and bigger and bigger and bigger. And typically, I don't know, olive oil has long chains of carbons like this, and those chains tend to be about 16 carbons long, and so on. So you can get these chains. You can get branched chains, and we're going to talk about that a little bit later. You can also get these chains going around in a circle and closing up to make rings. So this is an example of this. This would be cyclohexane. So the hex refers to 6 carbons, and the cyclo part refers to the fact that it's in a cycle, obviously. Yeah? Carbon tends to be pretty much unique in being able to do this. You kind of think that if carbon is able to form these long chains, then all the elements around about carbon in the periodic table should as well. But it turns out that that's not really true. Nitrogen kind of does, but if you make compounds with lots of nitrogens in a row, they tend to be very good explosives because they're not really very happy that way. They tend to just go bang. Boron doesn't either, and if you go down to silicon, silicon doesn't really either. So carbon's pretty much unique in being able to form these long chains of almost infinite length, where you just have carbon-carbon bonds all stuck together. Yeah? These pictures aren't too important. But if you're still drawing them down. I suppose one thing I could point out, just while we're here, in case it's not in a later slide, is that we have the shorthand thing that we do to save drawing out all the carbons and the hydrogens, right? So say, for butane, let's say propane. So here's propane. The shorthand that we use goes like this. It says we're not going to draw in any of the hydrogen atoms or the carbon atoms as such. We're just going to draw this molecule like that. Right? Can you see that? Obviously that's a simpler way of drawing it, so long as you know what it means. Yeah. So the idea is that if we draw those 2 lines like that, each of those lines represents a carbon-carbon bond. The join between the 2 lines and the ends of the 2 lines, because we haven't specified it as being something else, we assume it's a carbon atom. And then we further assume that all of those carbon atoms have 4 bonds, so any of the other bonds that aren't drawn in, we assume are bonds to hydrogens. Yeah, does that make sense? So So that would be the one for propane. If we had this molecule, like that, then we would draw this like this. Yeah? You see how that works? Because now we put the O and the H in here because this isn't a carbon. We only don't draw the label in if it's a carbon atom. And here we put the H on here, so we assume then that this carbon has an OH on it, so it's got a bond to this carbon and a bond to this oxygen. So there must be two other bonds here, each of them to hydrogen atoms. But all of that is assumed that you can understand from those sorts of pictures. Yeah? Hello?
What about methane?
Methane. You don't tend to use this for methane. Okay, that kind of makes sense? It's something, I don't know whether, do we see this at school? A little bit, maybe? No? You're going to see that a lot here. You see it in the books a lot as well. And the thing is, if you've got little molecules like these, then this is relatively straightforward. But if you've got big molecules, then it's more helpful to draw it this way because it's just hard to stick all the carbons and hydrogens in everywhere. There just isn't room without the picture being like this big. Right? Okay. Ooh.
What if the OHs attach on the other box, not all of them?
Yeah. I suppose the other thing is that we draw them at angles where this angle is roughly 120 degrees, and even though it's 109 degrees in the real molecule, the angle tends to be like that. I think mostly because it ends up giving you nice-looking pictures. I don't think there's any better reason for doing it than that. So, okay, the molecules with more interesting reactivities, assuming that just carbons and hydrogens are boring because they're all bonds that aren't really very reactive because they're strong and they're non-polar, the molecules with more interesting reactivities tend to be those where you have other atoms like nitrogen and especially oxygen attached to the carbons, right? So like this one, where you have an oxygen attached to the carbon somewhere. And the reason why, if you put an oxygen or a nitrogen in your molecule, this is a way of getting some reactivity there, is because putting an oxygen or nitrogen in will generate a polar bond, right? The electronegativity of oxygen is 3.44. The electronegativity of carbon is 2.55. And so we would say that a carbon-oxygen bond is polar. So there you go. That's almost a difference of 1. But this is definitely a polar bond. And so that means if we write a carbon-oxygen bond in a molecule, like we might do here, let's put this back on the end. Then we can put in these little partial charges that we talked about in the first week. Yeah? The oxygen is more electronegative than the carbon, so that means the electrons in this bond, this covalent bond between the carbon and the oxygen, tend to spend more time at this end, attracted to the oxygen because it's got the higher electronegativity. And so we could say that oxygen has a little partial negative charge on it, and so the carbon has a little partial positive charge on it. Yeah? You talked about this stuff yesterday as well, yeah? We're talking about dipole-dipole interactions and stuff. Yes? Cool. So we can write our carbon-oxygen bond like that. So it's a polar bond. Same with nitrogen. Nitrogen's electronegativity is a little bit smaller, so it's not quite as polar a bond, but a polar bond nonetheless. Because the ends of the bond have partial charges, then these can attract charged ions or other polar molecules that might be swimming by in the solution. Right? Dipole-dipole interactions, that sort of stuff that you talked about yesterday with Curie. And so this, in turn, can lead to a reaction happening. Right? So if you have a molecule like this, where you have a little partial negative charge here, then that can be somewhere where something with a positive charge can come and be attracted to this part of the molecule and cause a reaction to happen. If you have something with a negative charge, then that can be attracted to this carbon here, which has the partial positive charge, and that can be a way to start a reaction happening. Right? We're going to see this a lot. So polar bonds tend to be the things which cause organic molecules to be able to react. So we call these parts of the organic molecules where the presence of oxygen or nitrogen leads to the formation of polar bonds functional groups, because this is where the reactivity of the organic molecule lies. Okay? So if the organic molecule is able to function in a particular way or react in a particular way, it's due to the functional group that's present in the molecule. Right? So the functional group is not this carbon-hydrogen skeleton framework thing. It's the interesting bits dangling off the framework. And what we're going to find is that regardless of the molecule that you have, if you have two molecules which have the same functional group in them, then they will undergo the same sorts of chemical reactions. All right? So regardless of what else is going on in the molecule, regardless of how many carbons and hydrogens and stuff there are, if you have two molecules which have the same functional group in them, then they're going to do the same sorts of reactions. Right? There are lots of different types of functional groups out there. We tend to only worry about 7 or 8 or 9 of them, but there are many more, which we will see a few more of in 191, and if you go on in chemistry into 2nd and 3rd year, then you'll see lots more. So we're just going to look at a handful of them, but what we find is that if you have molecules which have the same sort of functional group, then they are named in that certain way. They're named in such a way as to be able to tell that the different molecules have the same functional group. And so they're grouped into what we call classes. So if you have two molecules that are in the same class, that means that they have the same functional group. And the way that you tell that they're in the same class is because there's a similarity in the names that we give the molecules. Yeah? So the first one's alcohols. So this is an alcohol. This one here, this is propanol. This is an alcohol. An alcohol contains the functional group C single bond OH. So if you have an OH group attached to a carbon somewhere and nothing else, then that's called an alcohol. So the class of molecule is an alcohol. And the functional group is the COH bit. Now, importantly, the way I've drawn the wee structure up there has the carbon with 3 other R groups on it. R is not some other atom, because in fact there is no R on the periodic table. R is another shorthand that we use to refer to other stuff that's not important. The technical name for the R is an alkyl group, at least it is for this year, and so that means more carbons and hydrogens, other parts of the framework, which in general will not have a functional group in amongst it. Right? So it's just stuff that's not important. The R can be a hydrogen, or it can be chains of carbon atoms. You're going to see the R thing all the time. So R, for example, could be a CH3 group, it can be an H, it could be a CH3, it could be a CH2, 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 CH3 group, it could be all sorts. But the key important thing is that it won't tend to have a functional group somewhere in it. It'll just be carbons and hydrogens. Yeah? So that's an alcohol. We're going to come back to alcohols a lot. Similar to an alcohol is something called an alkyl halide, or if you like, a haloalkane. There seems to be 2 schools of thought about what you name these things. So this is the same deal, except instead of having an OH group attached to your carbon, you've got a halogen, okay, where the halogen is just the name that's given to the elements in group 17 on the periodic table: fluorine, chlorine, bromine, iodine. So if you have one of those attached to a carbon, then you've got what's called an alkyl halide. And what you know about certainly fluorine and chlorine is that they're very electronegative elements. Fluorine, remember, is the most electronegative element. And so that means that if you have a fluorine in there, then that carbon-fluorine bond will be very polar. And so you would imagine very reactive. In fact, it's not, but you would imagine that it should be at least. Okay, so alcohols, alkyl halides. Then down the bottom we have amines. So an amine is a compound now where attached to that carbon we have a nitrogen. And that nitrogen in turn can have two hydrogens attached to it. But the nitrogen can also have two carbons attached to it, or one hydrogen and one carbon. Doesn't matter. Those would all be called amines. So I suppose, if you like, we could in general write amines like this. We could have C, R, N, R. Right? So those would be amines. We've said that carbon always has 4 bonds to be a stable, happy thing. In general, nitrogen will have 3 things to be a stable, happy thing. It's a little bit less clear-cut because nitrogen can have 4 things and still be relatively happy, whereas carbon can never have 5. But normally nitrogen's going to have 3 things attached to it. Yeah? So those are amines. And then we start having some slightly more complicated ones. This is what's called a carboxylic acid. Of course, we've met these already because we've talked about ethanoic acid a lot last week when we were doing the acid-base chemistry. Ethanoic acid is one compound in the class of compounds called carboxylic acids. And so they have a functional group which has got a C double bond O, and then that C has also got a single bond to another O, which is part of an OH group. So you have the COOH, as it's normally sort of said, functional group. Another thing which we talked about at this meeting yesterday quite a lot is the fact that people tend to not quite work out that even though the functional group is C double bond OOH, this C double bond O part, which we're going to see cropping up in lots of functional groups, this little bit here just itself has a particular name. Does anyone know what this is called? No, not just C with a double bond to an oxygen. Just that bond, if you like. It's called a carbonyl group. Have we heard this word? Yeah, see, this is high school chemistry apparently, but no one knows it. And we're just going to say it to you all the time and think that you know it. So just a C double bonded to an oxygen, regardless of whereabouts you might find that, whether it's in a carboxylic acid group or whether it's in a different sort of functional group, these are called carbonyl groups. Yeah?
How does that notation using R differ to that other one you were...
Here, R would just be something like this. Yeah, so this is just representing carbons and hydrogens. But in this particular case, it's representing 3 carbons and 7 hydrogens. That R can represent anything but carbons and hydrogens. Yeah? Okay, so that's a carboxylic acid. Then there's something called an ether. An ether is now where, if you like, you've got a carbon attached to an oxygen, but that oxygen, instead of being attached to a hydrogen, like you get in an alcohol, the oxygen's attached to another carbon. So you have an oxygen, if you like, bridging 2 carbons and their associated other stuff, the hydrogens and whatever. You don't tend to see ethers so much at school because ethers, by and large, are a bit nasty and explosive and dangerous. So that's them. And then we have aldehydes. So now an aldehyde has a carbonyl group in it again, the C double bond O, but the carbon of the carbonyl group has on one side of it another carbon or an R group, and on the other side it has a hydrogen, right? So a CHO is the way it's said, as opposed to a COH, because that tends to be how we say an alcohol. We call these ones a CHO functional group, an aldehyde functional group. So the carbonyl carbon's got a hydrogen on it, as well as an R group. The one that goes with this is something called a ketone, where a ketone has a carbonyl group, but the carbon of that carbonyl group has carbons attached to both sides, right? So no hydrogen now. It's an R, C double bond O, R. So that's those. There's a couple of other ones that we're going to come to tomorrow, which are sort of a little bit less important. But then there's also a couple where, sort of contrary to what I've already said, are functional groups where you don't have any oxygens or nitrogens. And so in these cases, these are ones where we have a carbon-carbon double bond, or, I believe, a carbon-carbon triple bond. We talked about this stuff when we did the Lewis structures, about how sometimes you can have 2 pairs of electrons being shared between 2 atoms, or even 3 pairs being shared. That can still be fine. It still gives you 8 electrons around each atom and all that sort of stuff. But a consequence of that is that it means that these, even though when you write a carbon-carbon double bond and you think about a Lewis structure of it, you would say that those 2 bonds are the same. The 2 covalent bonds are the same as each other. It turns out that they're not. And they're not for reasons that we don't really get into at all in Chem 191, but we do a lot in Chem 111, the second semester paper, right? One of these is what's called a sigma bond, and the other one's what's called a pi bond. And I suppose the important difference, that for as much as it matters for us today, is that one of those carbon-carbon bonds is much weaker than the other one. All the stuff we've been talking about how carbon-carbon bonds are strong, applies to one of those bonds in this molecule, or indeed one of the carbon-carbon bonds here. The other one, or the other ones here in an alkyne, are actually much weaker. And so you can break those bonds and do chemistry there much more readily than you can at just a carbon-carbon single bond by itself, right? So when we do reactions here, we break one of the carbon-carbon bonds, the weaker one, but the stronger one stays intact. Does that make sense? Yeah, we're going to see this tomorrow when we start talking about some reactions. And so alkenes, which are compounds which have a carbon-carbon double bond, and alkynes, which are the ones that have a carbon-carbon triple bond. Those multiple bonds, the double and the triple bonds, are also sites of reactivity because some of those carbon-carbon bonds are much weaker than the other ones. Does that sort of make sense? Yeah? Like I say, the reason why they're weaker is not something that we can do unless we talk about something called valence bond theory, which is well beyond anything we do in 191. Okay? But still note that in both of these, all the carbons are forming are attached to 4 things. They're forming 4 bonds. They're forming 4 bonds. They're not attached to 4 things necessarily. In the case of an alkyne, each of the carbons is only attached to 2 things, but it's still making 4 bonds. Which is our little rule that we said had to be followed. So we have this variety of classes of organic molecules, and like I say, this is only a little bit of them. There's lots more than this. Each class has its own particular functional group. The way in which each class of molecules reacts is characteristic of the functional group it possesses. right? So if you are an aldehyde, you do certain things. If you are an amine, you do certain other things. Amines don't tend to do the reactions that aldehydes do. But one amine will do the same reactions that another amine will do. Yeah? So the things are grouped together by functional group, but in effect we're grouping them together in terms of their chemical reactivity, just like the periodic table. Yeah? And we're going to see lots more about this we're going to see more about the reactivity tomorrow, and we start talking about what these characteristic reactions are, but then we're going to see lots more of it, like I say, in the second half of 191.